Okay, first a correction. When I started the previous video, I said we were in chapter 7. We're actually in chapter 6. Sorry about that. My video editing capabilities are a little bit too limited for me to go back and change that. So it'll be in the blackboard under chapter 6. So probably nobody will notice but me. Anyway, this is a fairly good depiction of how an enzyme works. Here's your substrate with a shape. Here's your enzyme with a shape for it to fit into. When it fits together, this part of the enzyme, or any part of the enzyme, something changes shape here. It's not, sometimes you see this drawn and the enzyme it just looks like a solid object that never changes. But it's the change in the enzyme, once this is stuck here, that causes the separation of these into separate sugars. The separate sugars don't fit in here anymore, so they come zipping off. And the enzyme pops back to its original shape, so it can keep doing this over and over and over and over again. Now, this will be a short video. And the reason for that is you may need to look at it a few times through the course of the semester. We're going to do a lab on enzymes that involves Michaelis Menten kinetics. We're going to talk about it later when we talk about other types of equilibriums, rate equilibriums for moving through a membrane, that sort of thing. Is that Michaelis Menten kinetics fits into a tremendous number of things in the world. And in fact, I'm going to give you an example that isn't an enzyme example, it's a real world example. So right now, as I'm recording this, the vaccine rollout for COVID is happening. So imagine you have a vaccine center and you've got 100 nurses or doctors, whoever you got, people that can actually administer the vaccine, stick the needle in people's arms. You have them set up in their little cubicles, and you have 100 of them. And people start to come in to get vaccines. So you have 10 people, you have 100 shooters. Easy. Get them done really fast. 20, get them done just as fast because you got bunches of people to do it. 30, 40, 50, 60, 70 people, 80 people, 90 people, even at 100 people, because they're being processed, they're going pretty well. But as you get more and more people, you hit a point where you have trouble finding I've got a person to get a shot. Let me find somebody who can give them a shot. They're busy, oh, here's somebody who's not busy. And so your rate of turnover, your ability to get people needled and out the door starts to drop off a little bit. You can't do it as quickly as you were doing it. And then you hit a point where you got a whole bunch of people waiting for shots, and every minute the people that are administering the shots are doing it. And no matter how many people pile up behind you, the people administering the shots are doing it as fast as they can do it. You keep giving them more people, but it no longer, the buildup of people behind you isn't having any effect on the folks that are actually administering the shots. They're working as quickly as they can possibly work. Their rate of getting people out the door with the shots has topped out. They can't go any faster, no matter what you say. Well, we got 500 people back here. Sorry, can't really do anything about it. That is Michaelis Menten kinetics at work. In this case, the reaction rate is represented as V. The number of people administering the shots is constant. You have a certain amount, that's what you got. So they're not changing. There's nothing here that's changing the amount of enzymes. Enzymes in this case are the people administering the shot. Enzymes are the molecules that are making the reaction happen. V, the reaction rate. What are we changing? We're throwing more stuff at them. And as often happens with these sorts of graphs, you don't put actual units on it, measurements, you just put an arrow. That should be a straight arrow. To show that the reaction rate is increasing if you go up this axis, the substrate concentration is increasing as you go out that axis. And so what happens as we add more substrates? Well, if we start with no substrates, we got no reaction. So we start right in the corner there. And as we add more substrates, we've got lots of enzymes to deal with it, and lots of enzymes to deal with it, and lots of enzymes to deal with it. Now the system's starting to get a little overwhelmed. You've got an enzyme available, but you're not necessarily able to find it as quickly because they're in the mess and there's too many substrates around. And the system starts to plateau, and then it flattens out. And no matter how many more substrates you throw into the system, the enzymes are all busy all the time. They can't work any faster. They can't get the reaction to happen any better than it's reacting. And you connect that point over to your velocity line. That's the maximum velocity. That's as fast as you can get it to work. Now they decided to not use that as a measurement to compare enzymes. They decided to take this amount and pop it in the middle, halfway point. So here's the halfway point. Come over to there, come down to there. At what concentration of substrate are you halfway to maxing the system out? Right? It's easier to, well, I don't know if it's easier to compare, but that's what they use to compare one enzyme's performance to another enzyme's performance. Is that at what point has the substrate hit half the concentration it would need to hit in order to hit half the speed of Vmax? A couple of other terms that work here. What affects how quickly the enzymes can work? How quickly can they grab the substrate? How quickly can they stress the substrate? How quickly does the substrate change and release? That's the affinity. The affinity is kind of sort of the stickiness of the enzyme. Can it grab, change, release, grab, change, release, grab, change, release? Higher affinity gives you probably a better Vmax. It also, you can do the affinity for the substrate and the affinity for the products. I mean, if it's somewhat sticky for the products, if it's not letting them go very fast, then it's not going to process as quickly. You get somebody on the line injecting the needle, but they make this big production over rubbing the alcohol on the skin and stuff, and it slows down the whole process, then your affinity is less. Another thing to keep in mind, if you have a multi-step process where you start with these substrates and you're ultimately going to get that product, but you have to change it in several steps, and you have an enzyme at every step. So you change A to B with an enzyme in between. You have B to C with an enzyme to do it. C to D with an enzyme to do it. D to E with an enzyme to do it. And E is the product of the pathway. Well, think about this. You got your vaccine station. It isn't just people coming in the door and going up and getting a shot. It's people coming in the door and checking in. It's people coming in the door and checking in and being given a form, and they got to fill the form out. And then you have steps. If it takes longer to fill the form out than it does to inject the people, then you're never gonna overwhelm the people with the needles because you're slowing down the process at the forms. Is that they're coming out of that too slow to really overwhelm the needle pushers. And so they're the limiting factor. Is an enzyme in the middle of a pathway can be the limiting factor if it slows down the system, or you have limited amounts of it. When you take Tylenol, the chemical that's actually gonna affect your headache is the product of a pathway in your liver. It's a several step pathway. You take the chemical out of the pill, and eventually your liver changes it into the chemical that's released to affect your headache. Enzyme, 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 enzyme. You have the least amount of enzyme in a middle step. So you change it, you change it, you change it. If you have put too much in at the front end, you hit this middle step, step C, say, and the enzyme can't handle it. Its Vmax is lower, its Michaelis Constant is lower. If you overwhelm the system, it can't change C to D as quickly as you need it to. Well, the problem with the acetaminophen is that C, that product in the middle, is very liver toxic. It can kill your liver if you let it build up. Under normal circumstances, you process it as soon as it hits that step. You got plenty of enzyme to process it if you're taking the right amount of Tylenol, if you're not taking way too many. Also, that particular enzyme has another job. It's involved in detoxification of ethyl alcohol. So if you're drinking liquor and taking Tylenol, you have two systems that are hitting that enzyme at the same time, and so it's easier to overwhelm it and to accumulate that toxic intermediary that can kill you. Is that an overdose of Tylenol can kill you pretty effectively because it can wipe out your liver, and there's not a heck of a lot they can do for you if your liver fails. You know, if it fails slowly, then you can get a liver transplant. If you go into a hospital with Tylenol poisoning, it's not like they got a liver there or a liver machine really, although they have been working on those to help you. So pathways can be affected by this, but a pathway has a bunch of different enzymes. Each one has its own Michaelis Menten kinetics. Okay, as I said, I want this to be on a dedicated video, so if you want to look at this stuff later when we talk about it, or later for the lab, it'll be available for that.